Thank you, Martin. Yeah. So just an addendum. First of all, let me add my welcome to that of Martin. Just an addendum to what he said about the trains. I think I brought it upon ourselves because a good friend of mine sent me an email saying good luck. And I replied saying, I don't need good luck. It's all so well organized. That were famous last words. And but I hope the two speakers who are stranded now in a taxi from New York to Durham will make it just in time for their talks. But my subject today is, by the way, Daniel Libeskind himself got stuck because of French restrictions in air traffic control, but he has just arrived, I know, so he will be speaking after me. So my job, though, is to tell you a little bit about, I'm giving the boring talk, about what kind of research we do at the Ogden Centre for Fundamental Physics. And as the name indicates, well, we worry about fundamental properties of the universe. And there are two strands to the research that we do here. We worry about the very small, and we worry about the very large, the two extremes. The very small is the domain of the Institute for Particle Physics Phenomenology. And what they are interested in is understanding the fundamental building blocks of matter, the forces of nature, the search for unification of all these forces and particles that we observe in the universe. And there's also work on dark matter. The very large is the domain so big that we are split into three very closely coordinated but administratively distinct entities: the Institute for Computational Cosmology, the Center for Extragalactic Astronomy, and the Center for Advanced Instrumentation. And what we're concerned with on the scale of the very large are the nature and the evolution of cosmic structure, the formation of galaxies and other structures in the universe, and we're very interested in trying to figure out what is the dark matter and the dark energy. Now, the two institutes that make up the Ogden Centre, the Particle Physics and Computational Cosmology, are now spread onto two buildings. Here is the building where the IPPP is that we used to share with them. And now we are in this building together with the Center for Extragalactic Astronomy and the Center for Advanced Instrumentation. But these two buildings make up the Ogden Centre for Fundamental Physics. Now, because we're opening the building, I'm going to tell you exclusively about what goes on inside the building, or what will be going on, what sort of research themes we have. So the questions that we ask at the Ogden Centre are among some of the most fundamental questions that we can ask as scientists. Questions such as how did our universe begin? What is it made of? How did it get to be the way it is? And what does the long-range forecast for our universe look like? And these are truly fundamental questions, questions that we're not the first to ask. I think questions that go back to the beginning of civilization. I would even say that civilization really started when our ancestors began to try to answer these sort of questions. Now, we have made some progress in the second and third of these questions. The first one is still an open subject for research for young physicists here. You might one day figure out how the universe began. We haven't got there yet. Our ideas about what does the future hold are also still very nebulous. But over the last 30 years or so, there's been quite a lot of progress in at least two of these questions. What is the universe made of? And how did it evolve to its present state? Now, science is great. It gives you surprises. And even the simple question of what is the universe made of has turned out to be really pretty, the solution, really pretty unexpected. It turns out that the contents of our universe are really very bizarre indeed. Only about 5% of what the universe contains is made of ordinary atoms, the atoms that we are made of, the atoms of the periodic table of the elements, the atoms of which planets, stars, galaxies are made of. All the normal matter that we know and love makes up only 5% of what the universe contains. About 25% is matter that is very different. It's not made of ordinary atoms, and it's called dark matter for the simple reason that it's dark. It doesn't shine in any wavelength of the electromagnetic spectrum. As far as we can tell, is pretty much completely dark. And as was discovered at the turn of the 20th century, the lion's share of the universe is something even stranger called dark energy. And the reality is that although we know quite a bit about that 5%, that's what chemists and biologists study, amongst others, we know rather little about dark matter and dark energy, particularly about dark energy. So let me just spend 30 seconds telling you about dark energy, because that's about the amount of time I need to tell you everything we know about it. And we know it's there. The dark energy must be there, or something like dark energy must be there. And that is simply because one of the most stunning discoveries of 20 years ago or so is the realization that our universe is not only expanding, but is expanding at an accelerating rate. The expansion is getting faster and faster and faster. It's what we call the accelerated expansion of the universe. So there must be something that acts against gravity, something, we don't know what it is, that's pushing galaxies away from one another, making the expansion of the universe accelerate. And that discovery of the accelerated expansion of the universe earned the 2011 Nobel Prize in Physics to some of our colleagues. And whatever it is that's pushing the universe, that opposes gravity, that's causing this accelerated expansion, whatever it is, goes by the name of dark energy, which basically neatly encapsulates our ignorance. When physicists use strange words like dark energy, you should smell a rat. It means we don't know what we're talking about. And that's pretty much the case here. Now, we know dark matter exists for many lines of evidence, but there are two in particular that are very compelling. One is simply the way in which stars move in galaxies, like the Milky Way. The stars go round and round the center of the galaxy. And it's very easy to see that the velocities of the stars are too large for the stars to be kept in place just by the gravity of the material that we can see. So the material that we can see in the form of stars and gas clouds does not produce enough gravity to keep the galaxy in place, to keep the stars moving at the speed at which they move. So there must be something else that we don't see, and that is pretty compelling evidence for dark matter. And there is another, even more, in many ways, compelling source of evidence, and that is the fact that dark matter, in fact, distorts the images of galaxies in an extremely elegant and pretty astonishing way. So here's a picture of a galaxy cluster taken by the Hubble Space Telescope, and you can see galaxies here that look just like galaxies should. These are the galaxies in the cluster, but if you look carefully, you can see that not only are there normal galaxies there are also these strange looking features that look like arcs, stretched features. These are also galaxies, but these are not galaxies in the cluster. These are galaxies that are a long way behind, whose light has been deflected by the gravity of the material in the galaxy cluster. And if light is deflected, then the image that produced the light is distorted in this characteristic pattern, which was in fact predicted in the 1920s by Albert Einstein. It's called gravitational lensing, and these characteristic patterns allow us to figure out how much mass there should be associated with the cluster, and the answer is there has to be about 10 times more matter in the cluster than what we can see in the form of stars and galaxies. So I have a little picture here of this is actually a real picture of the universe. This is the deepest picture ever taken by humanity with the Hubble Space Telescope. It's called the Hubble Deep Field. I'll come back to that in a minute. But we've done an experiment with it. We've imagined some big lump of dark matter in front of this pattern of galaxies. And you're going to see here what happens to the galaxies as the amount of mass in this lump of dark matter grows. So you see how it begins to distort galaxies. It pushes them out. It's just optics, it's just lensing, and it produces these patterns that we see in the famous picture of this galaxy cluster. So we understand how lensing works, and not only does it give a beautiful demonstration of general relativity, but it also allows us to tell that there is a lot of dark matter associated with the cluster. So the image one should have of galaxies is, as illustrated in this cartoon, a little pool of light embedded in a lump of dark matter, which for some saintly reasons that I never understood, we don't call it a lump, we call it a halo of dark matter, but it is really just a lump of dark matter inside which galaxies reside. So we know that dark matter is there, and we know that dark energy is there, and of course we know ordinary matter is there. So I think we've answered this question partially, because we don't really know what the main constituents of the universe are, but at least we have a name to describe them. Now, the next question here is, how did the universe evolve to the present state? And if you found the contents of the universe strange, well, it's even stranger. And so let me start at the beginning with the Big Bang. And here's a cartoon that illustrates the evolution of a universe from the Big Bang, shown here symbolically, all the way to today, 13.7 billion years later. So I'm going to give you a whirlwind tour of what happened in the Big Bang, just illustrating a few landmark moments in the history of our universe. So the story begins at the earliest time at which physicists can talk about physics, and as Martin Rees likes to say, and keep a straight face. And that is actually a very early time. It's 10 to the minus 35 seconds after the Big Bang. That's the earliest at which we can talk about physics as we understand them today. And there is evidence that I will show you later that something very strange happened at this time. The universe, for reasons that we don't fully understand, underwent a phase of very rapid expansion known as inflation. So a little patch of universe here inflated and grew from being the size of an atomic nucleus to being the size of a football in a very small fraction of a second. And we call that inflation. Now, inflation is driven or is produced by quantum phenomena and by quantum fields. Quantum fields have the habit of fluctuating in energy up and down. And one of the outcomes of inflation is that the universe is seeded by small irregularities known as quantum fluctuations, which make the universe have little patches where the density is slightly higher than average, other patches where the density is slightly lower than average. And the amazing proposition of modern cosmology is that everything we see in the universe, galaxies, stars, planets, even us, once came from a quantum fluctuation. And I can see Nina and Daniel coming. Hello, and Noam. Welcome.
Thank you.
Yes, I'm so pleased you made it. And there's Noah. Noam, hello, Nina. Nice to see you.
Hello.
Daniel, great to see you.
Good to see you. Thank you.
Yes. So he's responsible for the building. And well, I wouldn't say he. I think he and she are responsible for the building. Well, welcome. And where's Noam? I saw Noam as well up there. Very good. Well, very nice to see you all. I'm glad you made it, in spite of the best efforts by the French air traffic controllers. So you defeated them. Martin Rees is trying to defeat East Coast Virgin trains. So then the idea then is that these quantum processes then seeded the universe with very small fluctuations. And these fluctuations are, according to the evidence I'm going to show you, the progenitors of the galaxies that we see in the universe today. So that's the first landmark moment, 10 to the minus 35 seconds after the Big Bang. That was the hardest part of this talk, by the way, because that's quantum fields and quantum fluctuations. It gets easy from now on. The second landmark moment happened a lot later in these units, but still very early, 10 to the minus 10 seconds after the Big Bang, when the universe had cooled enough that particles that would be ideal candidates for the dark matter might have been created. So at this very early time, particles came out of energy, of the energy of the Big Bang, that could provide the dark matter that we see in the universe today. So that's the second landmark moment. And the third one is very important. It happened 350,000 years after the Big Bang. It sounds like a lot, but the universe is 13.7 billion years. So if you scale to a human lifespan, 350,000 years would correspond to one day in the life of the universe. So it's still very young. And something very important happened here, and that is that the Big Bang was hot. There was lots of radiation around. But at this time, the radiation was able to escape from the fog of the Big Bang. And that is the first light emitted by the universe. So it was emitted when the universe was a mere one human equivalent of 1 day old. And that light, which is nothing less than or more than the radiation of the Big Bang, was then free to escape and propagate in the universe. That light then brings us news about what the universe looked like at this very early time. And I'll come back to that in a minute. I'd just like to point out that the universe has been around for quite a long time, so this radiation has cooled. And because the universe is so old, today we see it at a temperature of just 2.7 degrees above absolute zero. It's very, very cold. It's in the form of microwaves. It's called the microwave background, the cosmic microwave background, and is light that has come directly to us from this very early phase in the history of the universe. It was discovered in 1964 by these two American physicists, engineers actually, Arno Penzias and Bob Wilson, who built a radio telescope and found radiation coming from everywhere. They had, in fact, discovered the first light from the Big Bang. Now, so that's the earliest we can examine our universe empirically. And it allows, this radiation allows us to make a test that these crazy ideas about inflation and quantum fluctuations may have some validity, because if the universe was seeded by these quantum fluctuations of inflation, then as the universe expands, then these fluctuations evolve. By the time the first light is emitted, these fluctuations would have altered very, very ever so slightly the temperature of this microwave background radiation, causing it to have patches where the temperature is slightly hotter and patches where the temperature is slightly cooler. And that phenomenon was predicted in the 1980s. The universe, the microwave background radiation should, it was predicted, have hot and cold spots in a characteristic pattern that physicists calculated. Here's a complicated curve. I'm not going to explain what it is. It doesn't really matter. Well, I can tell you what it is. It's just the temperature difference between 2 points on the sky. It's a function of how separated they are. The point is, these are theoretical predictions made in the 1980s, and then it's not just a straight line. They have features. They're complex. Well, 1992, in fact, to be specific, the 24th of April of 1992 was a milestone date in modern science, because NASA published this image taken by the COBE satellite, which shows the temperature of this relic radiation left over from the Big Bang. And as you can see, it's not uniform. It has hot and cold patches. This radiation was remeasured a decade later by another NASA satellite, which measured the same thing, but with much higher resolution. And then, of course, the Europeans catching up a decade later, but doing it better, launched the Planck satellite, which measured this microwave background radiation with exquisite accuracy. The Planck mission just finished in the last few months, and it has already reported its data. And what this data tell us is just simply amazing, and it's not an exaggeration to use that word, and that is shown here, which is one of, I think, the most impressive images or plots ever in physics. So what's shown here is that those funny predictions that I show you, made in the 1980s, about what the temperature of this background radiation should look like, about this pattern of hot and cold spots. It's a mathematical way to describe this pattern. So that's the green line. The green line is a theoretical prediction based on the concept of inflation, based on the concept of quantum fluctuations and dark matter. And the points here with arrow bars are the experimental measures. And you can see that the data agree perfectly with the theoretical predictions. And every time I show this plot, I like to pause for a second, just out of respect, because this really represents, I think, one of the greatest achievements of human civilization. Because for some reason, there are these species that's evolved. here in a galaxy, or like any other galaxy, capable of using their understanding of nature to make predictions for how the universe began. That's the green line. And the same species is capable of building machines that they launch out of their planet that can make these very, very fine measurements, because the signal here, the temperature difference between one point and the other, is only 1 part in 100,000. So these are exquisitely delicate measurements, and it agrees with the theory. So it tells us that, crazy as these ideas might sound at first sight, they're at least validated by these data. And so we can then ask, well, next question, of course, is, fine, the universe was seeded by quantum fluctuations, but what do they got to do with galaxies? How do we know galaxies came from these quantum fluctuations in inflation? Well, that's actually a much simpler problem to solve. And in order to do that, we need to understand the nature of dark matter, because dark matter then plays a huge role in amplifying these small fluctuations reflected here in the microwave background, and drives slightly denser patches, denser than average, makes them grow. I'm going to show you a movie in a minute, and amplifies these small fluctuations by enormous proportions to eventually produce the universe of galaxies. So how do we know that? Well, we just need to use the laws of physics, which is the only tool we have, and see what the laws of physics tell us when we try to evolve forwards in time these small fluctuations. Now, the problem is not particularly complicated, but it is sufficiently difficult that it can only be solved using large computers. And this is one of the things we do at the Ogden Centre. We do simulations of the universe. I'm going to tell you how to make a virtual universe. Don't do this at home. It's dangerous. What we need to do, or what we do, is we need to start from some initial conditions, which are those patterns of hot and cold spots. We need to make some assumption about the nature of the dark matter. And then we just need to instruct the computer, make a physicist out of a computer, teach the computer how to solve some basic equations of physics, general relativity, mechanics, radiative hydrodynamics, atomic physics, and so on. There's more, but these are just mathematical equations that computers are very good at solving. We feed those into the supercomputer, and here in Durham we have some of the largest supercomputers in the country, which only do one problem. They make virtual universes. That's their only mission. And you then feed some initial conditions, some assumptions, we know those, some assumption about the nature of the dark matter, and you just sit and wait for weeks, sometimes for months, and hope that you don't have a bug, which usually we do, and see what comes out. So let me show you an example of what comes out of these simulations. I should just say that key assumption is what is the dark matter, and the standard model of cosmology assumes that the dark matter is a particular kind of particle that, for reasons that I don't have time to explain, is known as cold dark matter. So here's a movie that we made very recently of a simulation. So what you're going to see is a patch of universe evolving from quantum fluctuations to the present. The expansion of the universe has been taken out, otherwise the screen would soon become insufficient to show the movie. And you will see first dark matter, then we cut to see ordinary matter, and then stars. So all that's coming here are these quantum fluctuations from inflation, the idea that the dark matter is some elementary particle, plus the known laws of physics. And so here is what happens. As time goes by, these small fluctuations are amplified by the gravity of the dark matter. Here we're just looking at dark matter. We're going to look at ordinary matter in a minute, and you see how the universe goes from being very smooth to being very highly structured. Here, a few billion years after the Big Bang, we cut to see what hydrogen gas has done. These gas clouds are spinning. They fall into these clumps of dark matter, which is not shown here. This is just the gas. But they're attracted. Some clumps of dark matter fall towards other clumps because of gravitational attraction. And you see that the gas settles into a thin disk. This is what the stars look like. We continue now the evolution. This is about 8 or 9 billion years after the Big Bang. and we're going to see what happens by the present day. And you can imagine what the outcome is going to be. This looks like a galaxy, and here it is almost at the present day, and we'll cut to stars in a second, and you will then be able to see what the computer produced just out of the laws of physics, simple assumption about the dark matter, and these quantum fluctuations from inflation. And this is one of many galaxies that we've simulated. And this really represents pretty much a breakthrough in the subject achieved here at Durham. Here is a gallery of some of the galaxies that came out of the computer. If some of you have looked at galaxies in the real atlas of the universe, you might find it difficult. These are not, to distinguish from these are not real galaxies. These are virtual galaxies that came out of our computer. So that's what we do at the Institute. Gosh, but we have also the Center for Extragalactic Astronomy observational colleagues whose job it is to prove we're wrong. So the role of the experimental side of the subject is to disprove everything I've been telling you. To do that, they study the galaxy distribution in great detail. This, again, the Hubble Deep Field that I showed you before. We're flying through it now, back in time as we do so. And our observational colleagues look at these images, and they can infer amazing amount of things from the data in telescopes, such as the rate at which these galaxies are making stars, the way in which they're being assembled. And let me show you this again, because it is really quite an amazing one very quickly, but we're looking billions of years into the past. So this, by the time this animation ends, we're looking at galaxies that were in the universe, these real galaxies, these are not from a simulation, about 2 billion years after the Big Bang. And as you can see, as we fly back in time, galaxies become smaller because they will grow later. They're actually bluer, which means that they are making stars at an abundant rate. So one of the great surprises of astrophysics in the last 30 years or so has been the realization that every galaxy, including our own, has a gigantic black hole in the center, something called a supermassive black hole. And one very active area of research at the new building is trying to understand how these black holes evolve, because it turns out that, tiny as they are, these black holes influence the development of the whole galaxy. So the study of supermassive black holes and the associated quasar phenomena are another very important topic of exciting research at the Ogden Centre. Now, astronomy, like every other science, is entirely reliant on technological innovation. And that is what happens also in the new building, where we have a group of very talented instrumentalists who have designed instruments for the largest telescopes in the world and have pioneered the application of many important techniques. I just picked one to show you here, and that is a way to sharpen images. So when you see a star twinkle, the star is not twinkling, the light twinkles because the atmosphere is turbulent and disperses the light. And that impedes the ability to study galaxies in detail. And wouldn't it be nice if we could somehow sharpen the images so that the twinkling due to the atmospheric turbulence was reduced? Well, that technique is known as adaptive optics. And here, the way it works is you shoot a laser out into space. You hope no airplane is coming nearby. And monitor with the laser the turbulence in the atmosphere, and then send the signal back to this many tons worth of telescope, and adjust the telescope ever so slightly to compensate for the turbulence in the atmosphere. I can see people look very skeptical. It can be done. I'll show you in a minute. And here is a picture of the laser designed here, the adaptive optics system, shooting a ray from the William Herschel telescope in La Palma. So here is the proof. Here is an image of stars taken from the ground with turbulence. And as we turn on the adaptive optics system, you can see how these images become increasingly, disappear in this case. They're meant to become increasingly sharp. Maybe we're going to have to use some imagination here. It's one of my movies that didn't work. Anyway, so the movie didn't take long, but you would see these images very, very sharply. Right, so now let me just spend my last couple of minutes telling you about what next at the Ogden Centre. of course, one of our main interests is to understand what exactly are these two things, the dark matter and the dark energy. As I mentioned before, we have a working model known as cold dark matter, but we have no guarantee that the universe did what we think it should have done. Maybe the particles that were created early on didn't have the properties of cold dark matter. There's a different class of particles known as warm dark matter, which are very different and produce different looking galaxies. I'll show you an example in a minute. Or the dark matter could be a lot more complicated. It could interact with other matter, interact with light, and we just don't know. And this is one of our main research interests. Now, we are astrophysicists. We look at what Desh has done. Of course, finding the dark matter is ultimately a problem for experimental physicists. And there's a big campaign throughout the world to try and detect these particles, because if they are what I think they are, this room is full of these dark matter particles, but they just go straight through our bodies. They don't interact with anything, which makes it very difficult to detect, because if you put a detector and what you're trying to detect just goes through, leaving no signal, well, you have a problem. Now, this dark matter can be detected. Occasionally, one of these particles would strike an atom in the detector. The experiments take place in deep mines in order to screen them from all the debris that rains onto the Earth from outer space. And here's a picture that I'm very fond of, because several people in this room appear in that picture, and you'll recognize some of them. Here's James Stirling sitting over here. He's the founding director of the Institute for Particle Physics Phenomenology. Here's Martin Simmons, who must be somewhere there. Here's his namesake, Tim Simmons. And here's, of course, Peter Ogden, dressed as a miner. So Peter, as you know, is a great supporter of physics at Durham, so much so that he went down to the mine to see if he could find dark matter. And sadly, he failed, but he's made up for that in many ways. Here's what he looks like normally when he's not looking for dark matter. And the amazing thing is that he's always smiling. Peter always smiles. And he didn't find the dark matter, let us down there, but he's compensated by helping us with the buildings, including the one that will be open tomorrow. So I take this opportunity, first of all, to thank Peter, Kath, the trustees of the Ogden Trust, for the tremendous support you've given us over the many years. Now, but it's not just Peter. There's also Damon De Laszlo here, who's another philanthropist, who, in fact, went down the mine. But Damon, we forgot a camera, so I cannot show a picture of Damon masquerading as a dark matter physicist. And Charles Jenks here, who's also one of our philanthropists, and there are others in the audience who wish to remain anonymous. Thank you to all of you, and we wouldn't be where we are without your support. So here is a computer simulation. I'm nearly done, Martin. Computer simulation of what the Milky Way halo should look like if the dark matter is cold on the left, or if it's warm on the right. And this is where the frontier of the subject is today, trying to distinguish between these two. You think it's easy for observational astronomers. Actually, it turns out to be really hard to see whether the Milky Way lives in a place like this or in a place like that, because the whole of galaxy formation is involved. So now, what about dark energy? Well, dark energy is another of our main topics of interest. The dark energy only becomes important relatively recently. So we don't know much about it, as I said before. I just have one slide, Martin, and I'll conclude. This slide shows you a famous equation in physics, this Einstein's equation of general relativity. I'm not going to solve it for you. I'm not even going to explain what it is, other than to say that this is one of the most amazing equations in physics. The left-hand side describes the geometry of the universe, the right-hand side, the content, the energy density of the universe. And there are two ways to try to make sense of the accelerated cosmic expansion. One is by adding some energy to the right-hand side of the equation. It's what we know by dark energy. But we have a very active group at Durham adding a term on the left-hand side, changing the equations of relativity in something called modified gravity, which may be, in fact, the answer to this dilemma, or to this great mystery of why the universe is expanding so fast. And here, predictions that compare the two, and if you have eagle eye, you can see that they're slightly different. Now, civilization, mankind, for some reason, has decided these are important questions, and they're spending billions of pounds, dollars, euros in missions to try and unravel these questions that I've been talking about before. And here at Durham, we're members of all these international collaborations, including, for example, the Next Generation Space Telescope that will be launched in a couple of years, another big satellite mission by the European Space Agency, and something that I'm very excited about called the Dark Energy Instrument Survey Instrument, which will actually tell us not just about dark energy, but also about dark matter. And of course, we have our computers and our intellectual capacity to think about the solution to these problems. So let me then conclude. There has been, as I hope I've shown you, tremendous progress in cosmology over the past 30 years. But I think the best is still to come. And we all hope that the Ogden Centre will be at the center of future developments. And I'll stop here.